university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success with Amrita University. A university where future is driven by imagination. Experiential learning creates diverse opportunities, where industry exposure and international partnerships help you sail. Come, start your journey towards success.
Stage or the floor to her. Dr. Alka Singh has a very illustrious educational background. She spent nearly 20 years in college, getting different degrees, adding several feathers to her cap, so to say, culminating in her getting a doctorate from the Technical University of Munich, Germany. So that was in November 2016. She had her doctorate thesis titled Dynamics of Water Mass Variations in Lake Reservoir Dominated Regions from Multi-Sensor Earth Observation Data and Hydrological Model Outputs. And after that, she was a research fellow, a postdoctoral research fellow in the laboratories of NASA, two of them, Jet Propulsion Laboratory and Caltech, Pasadena, California. Following that, at the NASA Goddard Space Flight Center, Greenbelt, Maryland, USA. So what was she doing before she got her PhD degree? I'll just go over the different degrees she has got to give you a flavor for her varied skills and interests. She has an MSc in computer science. She has an MSc in geoinformatics. She has an advanced diploma in remote sensing and GIS applications. She has a master's in geography, postgraduate diploma in computer applications, bachelor's of science in chemistry, botany, zoology. So that's the stellar galaxy of her accomplishments. And we are so glad that she joined us a few months ago at Amrita Center for Wireless Networks and Applications, the research center at Amrita Vishwavidyapeetham or Amrita University here in India. I would give you more details about the university and about the center. In the break, we're going to have like two parts to Dr. Alka Singh's webinar today. So, in between the two parts, I'll give a brief intro to the university and the center. So, with that, without much ado, I would now like to hand off the floor to Dr. Alka Singh.
Thank you very much, sir, for the kind and elaborate introduction. Welcome everyone to our webinar today. So let me share my screen. I hope you can see that.
Yes.
Like Sir has said, today's webinar is on exploring Earth from satellite remote sensing. In Amrita, we have a master's in geoinformatics, and we explore Earth from remote sensing also. So what remote sensing actually means, so as the name suggests, it's remote sensing. So we are observing something remotely. We are observing from distance. It's like a camera on our head. So Earth is observed every minute by a set of cameras rotating around Earth. So like we see a glimpse of it from this picture. It's like it's different cameras from different perspective with different rotation and orientation and whatnot. So all different cameras are looking different features, and there are some sensors or missions which are called geostationary, which means they stay stationary to Earth. But what it means, in other words, it focuses on one part of the Earth. If one region is under focus, the camera is looking at one part of the Earth, and it rotates with it. So likewise, it sees just one part, but all the time the eyes are overhead. But it also means it doesn't see other part of the Earth. So that's the geostationary satellite. There are other set of satellites which are mostly they are polar orbit. So the polar orbit satellite means what you see here in the picture. They rotate along the pole. So it's like they have paths. So they go through from here to from up ascending and then descending paths like this. So they keep on rotating Earth like this. So because it's rotating, it keeps on revolving also like this and like that. Not revolving, but rotating around and moving. With this, it has a repeat pass. So it has a data gap. So it sees this part of the Earth, but then it takes a while to get back to the same part of the Earth. So some satellites have like 2 hours of data gap, which is like very fast repeat pass. But some has like 6 months or like that. So some like I'm talking the two extremes. There are many of 16 days, 4 days, 8 days, likewise. So there are different satellites. They have different speed, and based on their speed, because it's like a trade-off. So if we are fast, we are not going to capture high resolution data, obviously. So we are going to we have to compromise between the resolution and swath and repeat path. So like that. So some satellites which are looking very closely, like very high resolution, then they go slow and they have to capture, because they have to capture so much in one go. And then there's swath. Well, by swath, what I mean is the screenshot. So like if we take if we think about a camera, the amount of area we are looking in will increase or decrease based on our swath. So based on what we say, the swath. So like for very high resolution image, swath is very small. Like we have very zoomed in picture of some part of if we take zoomed picture of anything, then it's a very small swath. But when we take MODIS, which is 500 to 1 kilometer special resolution, then it has a bigger swath. So because it has a bigger swath, it can move on fast, and because it can move on fast, it has no smaller time gap, which is higher repeativity. So there are different missions with different configuration of this kind. All these missions are not sent by one agency, but it's a group of agencies from different countries, and they not only send their own satellites, but also collaborate among each other. Like we have in India's Indian Space Research Organization, which is ISRO. US has NASA, which is National Aeronautical and Space Administration. European Space Agency, which is from Europe. Japan has Japanese Aerospace Exploration Agency, JAXA. So Canadian Space Agency, Russian Space Agency, Chinese Space Agency, so on and so forth. All different space missions are launched by different agencies, and they collaborate also so some missions are launched between Indian and NASA collaboration, or Indian or French mission, like that. So this French group, which is under ESA. So like that, we have a huge number of satellites rotating overhead, and they are observing different perspectives, different variables of Earth. So this all started way back during World War. As we all know, all these things happened not for the sake of Earth observation, but to spy other country or neighbors. So at that time, it was basically airborne. It didn't have that kind of technology to make it at the satellite level. But gradually, so initially it was like Sputnik and Explorer. All these were US. So Sputnik was Russian, and Explorer and NASA initiated missions. So they were like very beginning of the satellite period or satellite missions. So and then it gradually from military to civil purpose. So the first in this line was, or the biggest or the biggest achievement of, let's say, Earth observation system from any agency so far is Landsat. The Landsat era started in way back in 1972 when it launched Landsat 1, and that's the satellite which is still continuously observing Earth, but not the same. Of course, the tool gets expired, but they keep on sending the other one, then another one, then another one. So we have Landsat 1, 2, 3, 4, 5, not 6, but 7 and 8. So now Landsat 8 is in the orbit, and 7 is still in the orbit, but there are some errors in it. But nevertheless, we still have observation from it. So like that, we have continuous observation. So after the certain period, they send another mission, but another proof of Landsat. So they have same basic structure. Now Landsat 9 is under. There are discussions going on. They are building it, so. This is going to continue. The biggest thing which Landsat offers us is it's for free, first of all. Anyone from anywhere can use it, and it's a reasonably good resolution. So it gives us Earth observation at 30-meter spatial resolution. So when we talk about spatial resolution, some of you may be not aware of it, this term, which is nothing. It's a fancy word to say about just how it's like what we say the resolution, or how is the pixel, how much level you can see the image it gets pixelated. So when you take for example from your camera picture, when you zoom in, and when you zoom at the highest level, it gets blocky. And that's the highest resolution. That's the resolution at which it can differentiate between two features. And that's the blocks, which we say this is the spatial resolution, the size of the block. So in terms of Landsat or INSAT, its spatial resolution is 30 meters. So which is from the beginning on, and it has improved so much. They have now fast wide range of radiometric resolution as well. So it has higher, wider range of bands and wide radiometric resolution like that. So it has improved, but it is continuously observing Earth with the same concept, and it's freely available. So, but then there were other missions also, like MODIS. MODIS is also free and has a good set of data set, but it is relatively coarse resolution, so like 500 meter to 1 kilometer spatial resolution. There are dedicated missions like SRTM. So SRTM is something which observes the elevation of the Earth. So it was a tandem mission, and it was something like it followed one satellite following the other one, and based on the distance between them, they estimated the topology, so the height or elevation of the of entire Earth. This was the first time we got DEM, digital elevation model of Earth, through SRTM. And then there were many missions. Now we have many dedicated missions to one particular technology, maybe hyperspectral, maybe radiometric, synthetic aperture radar, or microwave, or any. I mean, there are multiple higher, focused to particular topic, like soil moisture, or dedicated mission for precipitation, for soil moisture, like that. So now we have many missions on board, and also now the private players are there. So there are commercial satellites which give very high resolution. Now we were talking about Landsat, which was 30 meter. We have now QuickBird kind of missions which observe Earth at 60 centimeters spatial resolution. So this is like the vast range of satellite data we have, and with different. It's just not about spatial resolution. I'm just talking about one thing, but there are different part of it. So how to understand that? Let's look into the basic physics of remote sensing. So it starts, like if we think about remote sensing, it starts from the energy, which is like at level A here. It is showing energy source. So where it gets the target is illuminated. Energy source can be sun, so where we get energy, and the reflected radiation we can observe through our sensors. Energy source can be the mission itself. So there are some missions which are called active missions, some are passive. So active are those which radiate their own energy. So they radiate they send signal to Earth, and that particular signal, when it bounces back and the sensor observes it, the change in the radiation energy, from that they estimate the features underneath. But there are passive sensors where they use the solar radiation, so they just observe the reflected sun rays and estimate the energy from it. So this is like these are two different kind of satellite missions, active and passive. So, but this depends. This definition, active passive, is basically coming from the source. So if the energy source is illuminated by the by sun or by the sensor itself, by the mission itself, the mission has its own source of energy. Then it has to pass through the phase. Then comes the phase B, where the radiation has to pass through the atmosphere. As we know, we have all these different kind of gases here. Gases coming. The gases like carbon dioxide, oxygen, all these things, they absorb or reflect radiations. Because of this, not everything coming from sun reaches to the target, or from the source coming from the sensors coming to the reaches to the target. So some get absorbed or reflected, and rest of it comes back. So this is a very important part where we have to take into consideration while planning any mission, or as understanding what kind of signals we are getting. So this is part B, where the atmosphere plays the role. And of course, the C is a target where it interacts with the target. So based on the interaction, only the reflection happens. If the target is water body, it absorbs a lot of energy. So based on it, the reflected energy is less, and then that's why the sensor observes darker side. So it has less energy, darker features we get. While some have like sand, or sun has a higher reflection. So it reflects that higher energy, and that's how we have a brighter side. So that's why we get different reflection, and based on it only we differentiate between two features, and we can interpret image and use it for any application. So this is a basic physics, and of course then followed the transmission, reception, and processing. So once sensors observe it, it's not going to keep it with it. It has to somewhere transmit it, and we have to store and process it, interpret it. This analysis part, which is actually going to happen in the lab and in any other organization. So this is not only for satellite, it's true for even airborne mission or even drones. So we have spaceborne way up. Then airborne missions are, space missions are above cloud, while airborne is sometimes below cloud. It depends on the cloud height. So airborne, and then comes drones, which are even below. We have all different heights at which we observe Earth. And these all are called remote sensing. So because we are observing Earth from distance, so it's remotely observing Earth is remote sensing. As I said, not everything which is coming to Earth is going to reach. So there are reflection, absorption, and that's what causes this kind of window. This is what we are seeing here in the figure is like from left to right. If we see it's increasing wavelength. So which means if we look into the electromagnetic spectrum, ultraviolet, then visible, the wavelength increases this way, and you see this spiky feature, and you might be thinking, what is it? I mean, energy is coming in all the bands when it is coming from sun. But what happens here when it passes through the atmosphere, because of the reflection and absorption, selective bands come to fall on the Earth. So it's like a few get absorbed by carbon dioxide, some get absorbed by some kind of gas, water molecule, all these things, they keep on absorbing. So this is called atmospheric window. Because of atmosphere, whatever is the gray, it cannot reach on Earth. So all these wavelengths cannot reach on Earth because of the atmosphere. And all these different colors are the atmospheric window. These are the bandwidth. These are the electromagnetic bandwidth which we can use to interpret different signals, different features, or use it for remote sensing or for any other application. And in this visible spectrum is a big chunk. You see here, which we have a bigger window open, and then comes the microwave range where we have bigger window. Other than that, this infrared thermal has limited bandwidth available for application of remote sensing. So this part is where initially most of the sensors focused, which is also Landsat. So here Landsat also uses visible part, that is, it has some bands which are red, green, blue, like that. It also has infrared band. Now we have Landsat 8, which also has thermal and other extra bands. So we use some part of these spectrum to make observation, and each separate spectrum becomes one band. And if we are observing multispectral, so which means we have many spectral bands. If we are observing through hyperspectral, we have very micro level changes in the band. So it's a very small bandwidth, and we are observing that. Like this, we define the mission. So here, what I talked here, you can see the same thing in a little more detail. So lower to higher wavelength, we go down. So this is a visible band where we have Landsat, SPOT, MODIS, all these missions with this visible spectrum, which uses visible spectrum. And then we have radar, SAR data, where we use the microwave spectrum, a part of the electromagnetic spectrum. If you look a little more detail of microwave, because we have wider window in microwave. Within microwave also there are P band, L band, F band, Q band, like that. We have different bands based on the wavelength and the frequency. So these bands define the kind of use we are going to do. So the application is like P band is more capable of like L band is used for vegetation where there is you want to estimate more the vegetation type, but rather like it doesn't have that much penetration. So these kind of within vegetation also penetration depth varies. So microwave on one side has an advantage that it penetrates through cloud, but then there are other features on the Earth, like there are dense forests, for example, in Amazon. So then some microwave sensors fail there because they can't penetrate to the through the plant. But then we have, based on the wavelength, we have different penetration depth. So these are the so while if we have visible spectrum or Landsat or all these missions which are multispectral, they are more prone to this cloud or weather disturbances because they cannot pass through these three. Their bands cannot, because they have lesser energy, so they can't pass through. While microwave has this advantage. So there are some advantage, but there are disadvantages of this kind because the microwave is difficult to interpret, and it's a different kind of concept. It's not right away. You can't read microwave images. It's totally. It looks like a gray salt and pepper image. So this is how let's say one Landsat image looks like. So different bands based on the what kind of what part of electromagnetic spectrum it has used. We define it band 1, band 2, band 3. So like blue, green, red, infrared, near infrared, thermal, like that. Then we can combine a couple of them, and based on our application, we combine sometimes the combination of red, green, and infrared makes one feature more prominent, while the combination of other, so for if we want to observe a water body, we combine infrared and red and let's say blue to get this feature highlighted. While for settlement or urban studies, we combine another set of bands. So this is called composite. So we combine them and highlight that feature and do the classification or change detection to identify what happened with this, to identify the changes and extract the features we are interested in. But this is like if we are using visible band or multispectral sensors like Landsat. But there are other sensors which are like microwave. They work on different concepts. Now, like what I said, we have we can take combination, but we can also take one band itself. So if we take just one band of Landsat, it looks like this, for example. I mean, it's just a subset. It's not a Landsat complete picture. Landsat has a wider coverage. So anyway, so the thing is, this is how a raw gray image looks like. So then we do some pre-processing. Let's say we just classify this image based on the reflection, or the simplest way we can classify by giving some threshold. Simply, okay, wherever the intensity of image is above this, I classify it as water. That's the simplest way we can classify or cluster the image that can create a lot of artifacts. So that's not the smartest way we want to address this. So for this, then we have to do proper pre-processing and then smart way of classification. So we can take it to the level of artificial intelligence and machine learning, but the simplest can be the isodata unsupervised classification. The classification happens based on the features, the reflection, and so some basic statistics. But eventually, we want to get rid of all these artifacts and get the clear feature extraction. This is like the processing of remote sensing, from raw to extraction of feature. We can go through the simplest way to the complex, to the most complex, like AI and all. This is all we do in our group. So, but there are so many other applications, and it started from defense, but it was just a beginning. Still, it's used. The remote sensing is heavily used in defense and intelligence, but nowadays we use it for natural resources like agricultural, forestry, hydrology, forest fire, different kind of natural hazards, flood, landslide, earthquake, the global warming, and the most common topic, climate change, sea level rise. All these things for this. Remote sensing has so much potential. It has wide range of application. It just depends on your imagination and how you combine different features and how you want to extract information from the combination of band or the electromagnetic spectrum, information coming from the electromagnetic spectrum. But yeah, I mean, we also have it for different development and construction, urban studies, law enforcement, navigation. This is just a small list, and it can go on and on and on. This up to now. I just talked about electromagnetic spectrum, which we used for remote sensing. Lately, since 2002, we have another mission. In space, which is called BRACE. So it's unlike other missions which uses electromagnetic spectrum. BRACE uses totally different technology. So it is based on gravity field. It's again like SRPM. It is a tandem mission, which means one satellite is following the other one, and what it observes, it observes the pull. So when these two satellites, they are supposed to have a 200-kilometer distance, and if they move in tandem over Earth like this. They rotate, and whenever there is a higher pull from underneath, let's say if Himalayas, if it passes through Himalayas, because it's a heavy body, there is a huge pull. Because of the pull, the first satellite gets slow. Because it gets slow, the distance between the two gets smaller. So eventually what we are interested in is the distance between the two satellites. Based on the distance between the two satellites, we inverse calculate, or this is inverse modeling they do. We calculate the amount of pull. So now we know the amount of pull from the Earth. When the first satellite came, and then it passes through, and then the second came, and it gets also pull, and so on and so forth. So then it moved. Okay, we know that there is a big gravity here, and okay, this is Himalayas. Then what's the use of it? Why are we interested in it? The thing is, if it is once, we are not interested. But it's going to pass through again and again. But next time when it passes through, if the change in the mass, or if the mass which it estimated, the pull it estimated is same, then no problem. But what happens, it estimates the change. So if once it moved and the second time the pull is less, there has to be some reason. So why the pull has decreased, that's the key. So then we think about, okay, why there is lesser gravity here compared to the previous day or previous pass. So because the repeativity of rays is like 1 month. So let's say what has changed, what has been different, what has been changing on this part of Earth in last 1 month, so that it's now lesser gravity. Lesser gravity means lesser mass. So lesser mass means what has changed. What can you think? What can change within a month from one part of Earth? If we would have been in the class, I would have asked you to guess, but I have to guess for you. So if we say, okay, what is circulating? Air is circulating. Maybe air changes. But if air moves from one place, then another part of it is not that there is a vacuum. So so this will circulate. There's other gas will refill that gap. So that cannot be the reason for change in gravity. But then the other possible reason, the thing which flows is water. Water flows, and if water moves from one region to another, then it's not that there is something going to fill it. So then there is a loss in this region, like what we are doing in when we are doing groundwater extraction. We are extracting water from underneath. So this is the mass of water which was pulling the satellite. Now this amount of water has been extracted and flown away from that region to another part of the Earth, and because there is precipitation, evaporation, so many other processes going on. Once we bring it to the surface, all different processes keeps working on it. So that's how we estimate change in groundwater through change in gravity, and that's like a remarkable and a revolutionary observation which we got through GRACE, which has changed hydrology, remote sensing of hydrology in a big way. So now we have estimation of groundwater depletion from North India, and in a big way that we are losing water from our northern part, India, and eastern part of India also, which is happening, which we can clearly see from GRACE. And this was never been, we were never able to calculate this because it's hard to close the water cycle. We had different models and estimations, but GRACE has revolutionized this by closing the water budget. So this is one kind of mission which gives another perspective to remote sensing. So that's about hydrology. And now we can also apply remote sensing in agriculture. Okay, we talked about hydrology, which is affecting through which we can estimate drought or other things also. But then it's when we talk about agriculture, that's we are interested in knowing what is the current crop pattern, what is going to happen, what is like we are always interested in forecasting what will be the production from this year. So this is like assessment of crop damage, crop production forecasting. Similarly, horticulture or cropping analysis. All different type of things can be done through remote sensing, through drone monitoring, through field equipments also, but also like missions, dedicated missions, like which are for soil moisture monitoring, for water, surface water estimation. All these things and combined with IoT and AI, and our institute is really good in these two, technology and clubbing them together. So we have, we scientific community have this expertise and we are exploring in that and we are excelling in that to estimate different kinds of variables like this crop pattern or crop production or even like horticulture and this is just one of the other applications for remote sensing. Another application, if we want to talk, I mean, we can go on and on and on, but another very commonly used remote sensing application is in hazards. So, like for example, flood. So we have a set of satellites which are called satellite altimetry. Satellite altimetry are they don't give images like we are seeing here. They give point observations, and it gives an estimation of water level, surface water level. Surface water level is interesting, but if we don't know what is the bathymetry, we don't know the volume. So what are we going to do with this? Again, the same concept. We don't have it just for once. When it passes through again and again, we see that there is an increase or decrease in surface water level. So this gives an idea of amount of increase in water, and that eventually gives a level to volume. So we know what is the amount of volume of water, or what is the volume of water upstream. If we know upstream water volume, increase in upstream or decrease in upstream water volume, we can estimate what is going to happen downstream, and we can maybe give a timely alarm and help people which probably get flooded. So like this picture here shows that this upstream area, and when they observe that there's a huge volume of water increase, then the same concept from same remote sensing data, you can see this is a regular flow of water, and then because the embankment, because the dam broke and the water gets flooded out, and this whole area which was normally not under flood zone got huge flood. So these kind of observation we can very nicely do through remote sensing. And it's not just that we see pictures, we also have a precise or very good estimate of water level. And so we have 3 dimensions. We have 2-dimensional image, we have height from water level, and through which we can calculate volume of water. And through when we know volume upstream, we can extrapolate it to downstream and do kind of forecasting and prevent a lot of damage to flood and prevent life loss like that. So there are so many applications. We can talk. The talk can go on, but I would like to bring you towards the demo part, so you can see how we use it in like real, like how do we download data, how do we process it, just a glimpse of it, and so that you can find interest in it and maybe you can try something. So before that, I'll hand over the floor to Setu sir, and I'll set up the demo for you.
Thank you.
Yes.
Thank you, Alka. So while Dr. Alka Singh is getting ready for the demo, let me give you a brief intro to the university and the research center that we are part of, known as the Amrita Center for Wireless Networks and Applications. Okay. So yes, let me share my screen and then I'll get started. Okay. All right. So we are known as Amrita Vishwavidyapeetham, like I said, or Amrita University. Vishwavidyapeetham means university in the Indian language of Sanskrit, as you might know. So, in terms of our vision and mission, we have 3 key pillars, if you will. Education for life, meaning we want to impart values so that what you learn actually helps you to lead a very healthy and strong life. Basically, prepares you for any eventualities in your life. Not only just give you the skills to make a living, we make you a complete person. And the second aspect is compassion. So all our research is driven by compassion. And thirdly, the research we do, we want the whole world to have benefits from it. That's why we call it as global impact. And all this vision comes from our chancellor, who is a very popular humanitarian leader worldwide, Sri Mata Amritanandamayi Devi, popularly known as Amma. Many of you might have come across her, even met her. So, what is this Amrita Vishwa Vidyapeetham? Just to give you a brief idea, it's a multi-campus, multidisciplinary university. So, we have 6 campuses currently. Amritapuri near Kollam, where we are located, Bengaluru, Chennai, Coimbatore, Kochi, Mysore, and 2 coming up very soon at New Delhi and Amravati in Andhra Pradesh. In terms of the different disciplines, we have the whole 9 yards, so to say. There are several disciplines in engineering. We have several. We have a full-fledged medical, college and hospital. State of the world-class hospital at Kochi, and one coming up in the New Delhi campus very soon, also. And then, of course, arts and sciences in many places. Sustainable development, very important for us, and also management. We have 4 schools of management in different campuses. So in terms of ranking, we are ranked number 1 private university, in the world, in India, by the THE, the Times, Higher Education Ranking, THE, right? Also by the QS World University Rankings, and then by the Indian government, the NIRF, National Institutional Ranking Framework, we ranked the 4th best university overall, not only private, overall 4th best in India. We are one of the institutions of eminence recognized by the government of India. Again, you might know that about 10 universities have been recognized as institutions of eminence. And more recently, the THE, the Times Higher Education, framework, they conducted a worldwide ranking based on the UN Sustainable Goals. Okay, and in that, Amrita came in the top 100 worldwide and number 1 in India. So those are really, great feathers in our cap, we believe. So sustainability, benefiting the society, compassion, these are the underlying, drivers for all our research and education as well. Now, coming to our center, the Center for Wireless Networks and Applications, call it in short as WNA. When we say we have a fundamental change in our research perspective, essentially the fundamental driver is compassion for us. What we do has to be beneficial to the society at large. That's the fundamental principle. So I'll just give you an overview of the kind of research that goes on. So obviously it's international caliber. As you will see, we have a lot of collaborations with international universities all over the world. So the solutions we develop are meant to solve real world problems of the society. And we do use state-of-the-art technologies for solving these problems. So because the problems we take up are complete problems, the research has to be interdisciplinary. So you'll see that there are different disciplines, people with different expertise that have come together at the center. And all this drives both our research as well as our education. The two are so tightly interconnected. In terms of the programs, the academic programs that we have a master's degree in wireless networks and applications. This has been running for about 12 years. More recently, we started a master's program in geoinformatics and Earth observation. So the geospatial technologies, GIS, how they are applicable, basically how the whole world, the ecosystem, everything is changing, and how we can study it, analyze it, and try to stem the degradation, if you will. All that, and of course, how do we address the sustainable development goals set by the United Nations? So all this is part of the charter of this program called Geoinformatics and Earth Observation. We also have a program in biomedical instrumentation signal processing, which was started just a year ago. It's also a very rich program. Again, we work closely with our hospital in Kochi. The doctors there in different specialities, we work with them and develop various solutions. I'll give you a glimpse of what we do later on. And we also have a PhD program. We have close to 26 PhD scholars working with us. And there's also what we call an integrated PhD program. So basically, you can combine your MTech with your PhD. and try to shorten the whole duration. So you can kind of optimize on the coursework, on your different stages, and etc. So potentially in about 2 + 3, 5 years, you could get your PhD along with your MTech. So when you talk about interdisciplinary, like you see at the left, we have mechanical engineers, electronics engineers, electrical engineers, AI, ML, that's like a backbone. Whatever all the different research we do, machine learning is very, essential aspect because we generate so much of data from all our sensors and all that. So it becomes really, very much a necessity that we use machine learning. Geology, of course, remote sensing, physics, wireless, all these are, different areas. We have interdisciplinary faculty, like I said, a lot of faculty with international experience, both in the academia as well as in the industry. We have 12 adjunct professors. So again, professors from across the globe who serve as adjunct professors. They do take, offer courses. They guide our students, etc. Both MTech and PhD students. We also have joint PhD programs, student exchange programs. I'll go into details of that. Dual masters programs, etc. There's also a program called Live-in Labs, wherein we actually go and we meaning the students, and not only our students from universities from across the globe. They come here to the university. They go to the villages along with our students and our faculty, understand the problems of the specific village and try to address those challenges. We have adopted 108 villages across India, and this is where we go and work in the field. That's why we call it a live-in labs. Okay. In terms of technology domains, I won't go into all the details, but all the latest and greatest state-of-the-art cutting-edge technologies are covered in all our MTech programs. We talk about extended reality, as they call it, XR, which is VR, AR, augmented, virtual reality, etc. All wireless technologies putting together, 5G, IoT, the latest Wi-Fi technologies, Bluetooth, you name it. Big data is a big thing, right? Software-defined networking, because everything is software-based these days. Geospatial technologies, GIS, so the satellite-based remote sensing, all these come together in all our programs. And a lot of emphasis on both hardware as well as software, because we always talk about building the complete system, not just one aspect of it. So just to give you again a brief idea of the different, some of the domains where these applications use technologies like 5G, IoT, AI, ML, big data, healthcare, e-commerce, robotics, IoT, automotive, industry, cloud computing. Just some, sprinkling. Again, in terms of job opportunities, again, in all these fields, you'll have job opportunities. So basically, what we call Industry 4.0, where, automation, real-time automation takes the center stage. So that opens up a whole new set of, skill sets. And that's the kind of skill sets that we impart to our students. Building distributed intelligent systems comprising of hardware, software, and networking infrastructure that binds all together. And there's a whole bunch of virtualization involved in this, right? What we talked about as extended reality, that's on the software visualization side. But there's also things like virtual machines, containers, network slicing, which is an essential aspect of 5G, etc. So we cover all those different things. Just a brief on our faculty. Dr. Manisha Ramesh is the director, and just to let you know, she was selected among the top 2% of the scientists in the world by a recent survey conducted by the Stanford University. Dr. Menon comes from DRDO, a lot of industry experience in India. Balaji and myself both have been in the US for a couple of decades working in the industry. Dr. Vadhavan comes from GSI, he was the Director General. Dr. Ravi Shankar comes from QSAT. And these are some of our younger faculty, who actually, grew with us. And some of them got their PhD from us as well. And some of them were also the toppers when they did their masters with us. More of these, Martin and Alka both got their PhD from Germany. You're listening to Alka in this presentation. Dhanya again, covers GIS, geospatial technologies, atmospheric modeling, etc., etc. Ram Kumar is more into virtual reality, augmented reality, extended reality, etc. Again, adjunct faculty, we have again a very impressive list. I won't go through the whole list, but it comprises of people from industry as well as academia from across the globe, suffice it to say that, and India as well. So, and many of them actually take courses for the students and guide the students also in their projects. In terms of the internship and placement record, it's pretty impressive as well. People do get to do their internship during the second year. It's a 2-year master's program. And the second year, there is an opportunity to do internship. So there are product-based companies, the one I have shown in green, and the IT companies in red. And the blue ones are the startup companies, and the yellow, if you will, are the education institutions. So people do get placed in all these different things, different types of institutions and companies. There's a lot of international opportunity. I think I mentioned it before. So you do get to work with international universities. There are dual degree programs, there are student exchange programs, etc. Universities in Europe, universities in the US. I won't go through the list, but you can take a look, and it's all there on the website as well. So if you can't catch all of it now, feel free to go to our website and take a look. And what are the possibilities for the students? They can publish papers in journals, for conferences. They get to do dual degrees in masters, integrated PhD. There is also a dual PhD that's possible. So basically, you can get a PhD from India, Amrita, as well as a foreign university. Same thing with masters. You can get a master's from Amrita as well as from a foreign university. Industry engagement, and then engagement with research institutes in India as well as abroad. So we started our center in 2006. I won't go through the details again. We've had some very nice milestones along the way. Even our Prime Minister releasing one of our products called Amrita Spandanam, which is a wearable device for measuring various vitals in the body. And we have our first landslide monitoring and detection system deployed in Munnar, and subsequently one deployed in Sikkim as well. And these are really flagship. There is also another project called OceanNet, which is to provide affordable internet connectivity to the fishermen. These are pretty much like world's first kind of projects. So coming to our research, we can kind of broadly classify the research into 4 buckets: IoT for extreme environments, wearable medical systems, smart city infrastructure, and immersive learning. And today's webinar about remote sensing, it plays a major role in pretty much all these areas. And everything we talked about, IoT, machine learning, 5G and other networking technologies, they all form the backbone for all these different applications, right? So what do we have under IoT for extreme environments? I told you about landslide monitoring systems. We have flood monitoring systems. Dr. Alka was talking about how satellites can be used to monitor floods, offshore communication for fishermen, and what's called multi-hazard risk assessment. When it comes to wearable medical systems, this is where we work closely with our hospital staff, the doctors there, and our MTech course in biomedical instrumentation and signal processing is an offshoot of all these different research projects that have been going on when it comes to monitoring the vitals using wearables, breast cancer detection and other disease detection using image processing. And there's also a lot of remote patient monitoring for COVID, in which we've done some work, and we get it deployed in our hospital in Kochi. When it comes to smart city infrastructure, there is a lot of, again, many of these projects are Indo-European, Indo-German, Italian. So like that, collaboration with a different country, institution in that country. So smart city, we have, water-based research. We have a lot of smart grid and microgrid-based research, etc. And finally, when it comes to immersive learning, how do we make remote learning, which has become an essential aspect of today's world in the COVID scenario? How do we make it more immersive, more catchy, more provide you better context, make you more getting more absorbed in learning as if you are sitting in the classroom? So that's the kind of research we do, and we publish some good work there. There's also work going on how do we employ augmented reality to reconstruct some of our heritage sites. So that was a brief on the research. I talked about the landslide monitoring, the world's first. We got many awards and many grants also. Similarly, for the OceanNet also, a lot of recognition. And then we have good laboratories. I won't go into the details. But again, some of the things mentioned here. Amrita Kripa is a disaster rescue app. Which can be used in the post-disaster scenario. We have some good laboratories. So talking about international projects, I told you, we have 10 of them. We also have 4 joint research centers set up with some international, institutions across the world, 25 research partners across the world again. It's a very impressive scene there. So we have 20 US patents granted, out of which 10 have come from students' work. So that's very impressive as well. And again, a lot of journal publications. In terms of averages, also we are doing very well per faculty and per PhD graduate. You can look at the numbers. So overall, and we have graduated 7 PhDs so far. So 20 US patents. I told you, how many people it has impacted. Some of them have become products also. Some of our research, turns into products. So it's also a key thing that to be mentioned. I talked about the COVID-19 research, so a lot of research with respect to remote monitoring of patients. And finally, I think it's probably the last slide on Live-in Labs. So the Live-in Labs program, I kind of mentioned it. We have adopted 108 villages in different states of India. So, we have our students along with students from other, universities and institutions who have signed up for this program, go to these villages and work on these different areas. There are 6 different areas mentioned there. You can see agriculture, education, energy, water, health, and waste management, right? So these are like the different silos that we have identified. So depending on what the problem is in each village, the students go there and then try to devise solutions for that. So I'll end with this note that, once again emphasizing that our research is compassion driven based on the vision of our Chancellor, Amma. And so I do, urge you people to go take a look at our website. And of course, do contact us if you are interested in joining us, either for the master's program or for the PhD program. We'll be more than happy to answer your questions and even, welcome you on board if you have the right skill sets and the right information. So with that, I will end this and I'll hand it back to Dr. Alka to continue with her presentation. Over to you, Alka.
Thank you, sir. Thank you, sir, for the detailed description of our institute. Like I'm seeing from a couple of questions, people are asking if we have collaborations with ISRO or government organizations. So yes, we have our students from geoinformatics last year batch. They got internship in ISRO, and even we have industrial internships from our students, and so they got they worked in ISRI, and now they got job also in a couple of them. They got job in ISRI. Also, not only here in India, we have our students went to like Lawrence Berkeley and other organizations abroad for internships. So like this, so we are quite. Our students explore different dimensions, not only within institute but outside, in government, in academia, everywhere, and in industry. So though it's the course geoinformatics started recently, but it's growing very fast, and our students are excelling in different places, and wherever they are working, they are well recognized. So yeah, you can check more about it through our websites as suggested. Now going back to our presentation or talk on remote sensing. Let me share my slide again. I must share my screen. So the idea of this demonstration is, I cannot teach remote sensing or talk about remote sensing as a whole in this small time, but I'll just give a quick overview. Like if you are just starting, how can you begin maybe? So like first step is to get the data. So where do you get data? So there are so many different platforms where you can, but there are some there are some recommendable platform where you can go, and they are very user friendly, and you can get many data from one platform itself. So I would go through a couple of them. So like first of course, NASA is the biggest player in this field. So I'll start with that. So one of the good browser or the explorer the NASA has developed is called Worldview. I mean, if you click this link, you can go there in order to avoid the internet glitch. I have opened this already. I opened all these windows. So when you click that link, the link will take you here. So this is what you will see when you click that link. This is just a welcome note, and then you will see this. So right now, if you say this, you might be thinking, what is this? So that's what I was saying, that this is a picture from Terra. So this is of course, this is the globe, the world map, and these patchy thing is actually the satellite passing through from from up in a polar orbit like this. It's rotating. So this was the morning picture. So this is a picture from today itself. You can see this region is cloudy. There is less cloud in Tamil Nadu. So this is this today's picture, which it took at one particular time. And you can see all these details from this website. Just to show you the path which I'm talking about. I clicked here, so if you go down, I hope you can see this, how you can click this option, and then you can check this ascending day, so to see the path. So this is how the polar orbit pictures are taken. So this is the satellite went through this, and again and again and again, like this. It is taking picture. If we look back to India, so partly it was taken by this part of it was taken at 4:45 a.m. So 4:45, and then you can see even the time spots here. So these are the clicks which the sensor that the satellite took. This is Terra mission. It's just one mission, but just to get a feel how really remote sensing takes picture when it is in polar orbit. It's like, and then if you click it again in the evening, after the class or the webinar, you will see another patch here. This is patchy because it's from today. But if I slide the window, let's say for yesterday or you can choose the date here, then you have a picture from the entire Earth. Now you will say, okay, I have it along the path. What about these gaps? So, which means probably one part of the Earth is never observed, but that's not the case. So, like if you remember from the last day, like today's picture, we saw there was some part of India, some part of observation missing from this region of India, while now this is missing. So, which means the path is not over each other all the time. It's around each other. So that's why it keeps on filling the gaps, and it's like keeps on rotating, rotating around Earth and filling the gaps and taking observation in this form. So this is the way you can feel that how remote sensing takes shots. Now this is just to get the feel. We don't need to see the path all the time. Now we want to look from maybe, let's say, other missions. We want to add some. So we can add some data from other missions, or we can choose from based on some discipline, or like hazard and disaster, science discipline, or like that here. Or we can use a filter window. Let's say I want to use soil moisture data. So for soil moisture, I can write here the soil moisture. And you see that there are different data sets. What are the different data sets available? You can see here. These are the different data sets, soil moisture data sets available. And you can choose one of it. let's say I choose this one randomly. So, but if I have it from, this will show a picture from today. And then now you see this from that day only, from wherever your cursor is, it will show the pictures taken by this mission, whatever mission we selected, and over the previous mission, because we are adding the layers. We can also delete layers, and we can combine multiple layers. So here again, we are seeing the pass, because it's passing, and there are a lot of gaps here, and some data is missing. So that there are other factors to it. So like soil moisture data is not continuous. If it is taken if it's just the remote sensing data, soil moisture is not continuous because it's radar based. So we learned already that there are different bands in it, and they have different level of they can go in. So that's why some region which are like a very highly vegetated region, like Amazon or even any other equatorial belt, where heavy vegetation is there, or so in many parts of the world, soil moisture is hard to estimate. Like even the estimation which is there may not be correct. For example, from Thar, very high, very dry region, or very highly dense vegetated region. So these are the limitations where we get this. There are limitations for different missions. This is we can add another layer just for fun. Let's say add population. Population density in 2000. So then here we have the population density map. Now we want to if we want to add, so this is like a platform where you can add different layers, see what is there for, and I mean you can choose, and when it is more useful, I would say it's because it's not a platform where you will be downloading data. You'll be exploring data in this platform. And this gives an idea of change over time in one go. So you can have a glimpse of the global change of any particular parameter. I mean, the population is quite a stationary variable. Let's change to temperature. So temperature, because precipitation was something which is, or precipitation can also be a good variable to take. So add layer. Now we have global temperature layer. So this you can see the global picture, and you can see the change over time. So maybe we don't want population; it is coming on our way, so we can remove population, close it, so that it's not coming on our way to understand the change in temperature. So that's like it's a sliding window. You can see the change over time. And okay, we are not interested in soil moisture. So you can simply close it here. You don't have to delete it. I mean, you can cut and delete it, but you can hide the layer also and see the change in temperature. Maybe you can also add precipitation here, and you see what is happening in these few days among these variables. So it gives a quick overview or how things are changing globally, and especially during some hazard or some event when you want to do some want to understand what happened before this event. You can quickly go to this browser, which is created by NASA, and see what is happening globally, or even you can zoom in and look into the one particular location. And see what is happening here closely in terms of whatever variables you want to add. So it's a very nice tool, or handy tool to have. Then I would like you to be introduced to the other tool, which is a Data Explorer, again from NASA. This is to download data. So you can download, for example, again, temperature. If we say we can search here, temperature. Just right here in the search window. So this is the link is there in the PPT, but you can just click the link. You'll get this kind of window. You can put it in the search window. Whatever variable you want to look into. Now you have all these given files are from are giving temperature information, but maybe you are interested in MODIS, or you are interested in let's say eco-stress. Eco-stress is another very cool NASA mission which measures the stress in vegetation, again through temperature. But it's very cool because it observes it can give an estimate of vegetation which is under stress, but not you can't see it through NDVI. Visually it's not visible that the plant is under water stress, but inside it is stressed because it's because of high temperature, because of less water, whatever. But these are under stress but not dried yet. So this precondition you already can see through this full mission, which is called eco-stress. You can. I mean, I'm just saying we can find all these temperature-related satellite observations through just checking it. You just browse it here. I mean, search it here, and the huge list of all different missions which observe temperature you can see. Like MODIS has a temperature observation, and so different. But then you may want to Google what is special in this mission. So what MODIS give us over eco-stress? What is there in Sentinel or any other mission? So based on it, you choose whatever you want. So to choose, let's say if you want to download MODIS data, so I click here, then all the granules are available. So I may want a selected time window. Then I can do some filtering here. Yeah, there's a filtering option somewhere. So yeah, here you have filters. So you can give the granules and temporal extent. Okay, I want it from this time to this time. You can put all these information here. And if it is recurring, you want daytime, anytime, or like that, you could give all the specifications, and based on it, it will shortlist the whatever number of days and months and kind of conditions you give. It will filter it and show it here. You just by one click you can put it in for download. I don't want to download all in general. I mean, everyone, most of us, and or maybe you want to just try. Then you can simply download by clicking it. Yeah, but remember, before you start for anything, it will ask you to log in. It didn't ask me here because I logged in before, so you have to register in NASA. And when you will click to these links, it will anyways ask you to register. And once you register and log in, then only you can download things. So you can simply click and download data, and then comes the reading part, which I'll discuss later. So this is one platform where you can get most of the data set. Another platform where you can get data is US. That was through NASA. The previous one was through NASA. The data search, while this one is from USGS. Again from US, but this is totally different independent organization called USGS. USGS manages Landsat. So because it's one of the most important data for common use, so that's why I thought it's important to discuss that. How do you download Landsat data? So you just click this link. Again, you have to log in. So you have to register and log in. I'm logged in, so it will let me do further activities. So you register. Everything is free. NASA has a protocol that they make. Their products are free, publicly available. So then you can set up, you can give the particular location. You can choose if you want to give a pinpoint. So if I say I want a centered location at this location, I want this location. This is the lat long where I want data from, and then you search for the day again from this day to this day. Then you may want to check about cloud cover, because Landsat data has a limitation that it cannot observe in the region where there are clouds. So we want to have cloud-free region, and this is a window where you can fill in. Okay, I don't want to have cloud anyways. I want to have like just 10% is okay if I'm okay with the 10% of cloud, or I don't want at all cloud, because probably you want to extract some feature which has cloud signatures which are similar to cloud. The white signature. Maybe you are looking into some sandy area, so it has white or bright reflection. Cloud can maybe confuse you, so you don't want it at all. Or maybe you are looking for something which is a distinct feature and a little bit of cloud you don't mind. So based on it, you decide how much you want, and that's how you will get images. Maybe there are more images, or repeativity will be affected by this kind of filter you set. So you can set the date and location, everything here, and then you can ask for the data set. There are data sets which are not only from Landsat, but from other missions also. And if we look into the Landsat archive, it has collections from level 1, level 2, and right now Landsat 8 and 7 is on board. It's still observing. But Landsat 5 is not there anymore. But the data sets are very good in quality, so we still use it when we have to look back in time. So I downloaded one sample data for you from Landsat 5 and Landsat 8, just to discuss and show you in the software. This is how where you will choose which data set you want. With Landsat 8 is new, and if you want to see something before that period, you have to look into previous data set. Landsat 7 has some error since 2013. So before that, it was good in observation. All images were good, but now still you can use it. But there are some striking error, which is essentially of scanner issue. So you choose this data set, and then you have a list of, and just to show, probably I can show you here. Randomly, I select some region here, just like that, and then I search data set. I said and then I if I want, I can set additional criteria, sensor, daylight indicator, whatever. I want cloud and all these things we can set, or I don't mind that, then I have results. So I might have set some, because I said that I didn't set the date, so I have to set time, maybe selected for today, and there's no observation for today. So anyways, without wasting much time here, you from this website, with a simple step, you can download Landsat data. And for other data sets, you can processed products also, they are available from a different model, remote sensing, like that. You can download it from Earth Data search website. So this is a very cool resource for US resources, for NASA project. For European Space Agency, there is another, because they are independent, they have their own, like we have in our, we have one for ISRO. For ESA, we have this ECMWF, which is, again, if you click that website, the link given in the PPT, this website will take you here, and you can select which month, which year, and which product you want to download. Monthly or monthly mean, daily mean, blah, 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 blah. And then you can select the parameter. So you can, by selecting 2-meter dew point. So this is model come remote sensing. This is a product which is ECMWF, which ECMWF provides. So these are the huge list of variables which you can download it from ECMWF. And that too, because it's a model product, you have a choice to select the time point. So you can time steps, you want it every 3 hours, every 6 hours, like that, and how much resolution you want. You can also choose that. So, for example, you select that, and don't select all. You select a couple of them, and select time point. Then it will give you just randomly. I'm choosing a couple of them, and then because I have not logged in, so it says please log in because to download. So then this is another website, and then you can also choose. I don't want to waste time here, so just you can like fill it. You can choose what you want. These variables are there, and you can also change the spatial resolution of the image, and then you have the data. For everything you have to, of course, log in before. Now you have data. What are you going to do with it? So this is all what I already discussed. Now we have data coming in different formats, and which is a big deal. So we have data coming in NetCDF, HDF, TIFF, and many different formats. And then it's very challenging. So data interoperability is still an issue. There are so many different softwares available. I'm just showing ArcGIS. As we already talked about it, we have a partnership with ISRI, and we have students as working there, like they got their job there after completing their geoinformatics, but also a couple of them did their internship there. So this is just because of it. I'm using ArcGIS because we have this software available. But you can read this data set in many different softwares. Like this like NV, it is again a commercial software, but also there are softwares like MATLAB, which is coding based. I mean, these are like a couple of clicks and you can handle it. But for a startup, but when you want to get expert into it, you will definitely move to some coding coding softwares. That's why one of you have asked if computer science is important to learn GIS. It's not that you can't do GIS without computer science, but it's helpful, definitely. And we have students from all different disciplines. And I mean, that's why it's an interesting course, because we have to start from scratch. Because we have students from agriculture, from electronics, from civil, from even geography and other disciplines students come. So we have to start from scratch, where we are talking from basics. So having computer science helps, but it's not mandatory. We will teach everything step by step. So we can. So here I am demonstrating ArcGIS, but we need to learn from how do we read it from other softwares also. But because of the time limitation, I'm not going in that detail for all these things. So like if you want to simply if you have this ArcGIS, ArcGIS is a commercial software. So if you just if you click ArcGIS, it opens like this, and it opens with where you have to click on map. I kept it open just to save time because it takes some time to load. So now when we want to add, let's say, Landsat image. So Landsat image is very simple. You just use add map and you browse to your folder where you kept your data. In this case, I kept it here. So we are running late in time. So quickly, I can show you just like this. You can read Landsat data. Like, let me just select a couple of bands and add it here. So that's just like you use add data option here, and it gets into ArcGIS. You have to select, of course, and then okay, because you're using first time Landsat, probably you don't know what is there, what is the special resolution, and you want to explore, want to understand. So then you have to. That's why I wanted to load everything, but because I want to show you also, that's why I had to keep this unless it's happening. Yeah, so this is taking forever. So yeah, there. This is one picture of Landsat. Now you can see this is so nicely projected in ArcGIS. You just click it and it's there. But maybe that's not so comfortable when you do it from, let's say, R or any other coding software. You may have to program a little bit. But of course, like if we program, we have more control. But these commercial softwares gives us a easy go platform wherein we just put you could have drag and drop also. And the stiff image can be read like this. You can swipe and see the difference between the two. For the time's sake, maybe I'll just show you the difference between one more. So this is Landsat. That was Landsat 5. Now let me open Landsat 8. One image only. Just for the okay. Now I want to see. Okay, this is same region. For the same region, I downloaded Landsat 5 and Landsat 8. Landsat 5 is from 2010. You can see the date here. That 2010 June. And 2020, 2000, no, not 2010, 2001, 2001, and 2021. So you see this is a gap of like 20 years, and with just one click here, you can see the difference. So you can see that water body here has increased. So in the last 20 years, something has changed in this region. So not something, but big thing, because maybe some canal and some new irrigation project. 20 years ago, this region looked like this. It's just one band here because of the time's sake I'm showing. Otherwise, I would have I had planned to make FCC or do some simple classification, but probably we can't go in that detail. So you can just read it this way, and just you can hear in the appearance there is a tool called swipe, and you can swipe it like this and see how things have changed in the last 20 years in this region. You can zoom in and see it in more detail. Like this, you can explore further in for Landsat. For let's say, I don't know if I should go. Maybe it's better if I take question and answer because of the time. Because we can also read. My plan was to read netcdf files and HDF files too. But I guess maybe you want to take, it's better to take some question answer at this point. Oh. So what do you say? Can we observe actually the images of satellite in Amrita University? Yes. I mean, we can observe the satellite images from anywhere because many of the satellite images are free. And in Amrita University, yes, we also procure images because we have a couple of projects from Government of India and abroad. So we have, those images which are free, you can observe from any part of the world. You need just a couple of softwares to help to support that. And there are also free softwares like R and Python. You can use those scripts to read satellites, so that definitely you can use it. And in Amrita, we additionally use commercial softwares and satellite data, which sometimes we need to procure. What is the best encoding algorithm for compression of remote sensing images? So why do you want to compress it? Everything depends on the purpose. So, I mean, you can use Fourier transform for compression. Remote sensing images as such is not it won't need any different kind of compression. As you do image processing in any other images, like even your computer, even your image which you got it through your camera, whatever image processing algorithm you can do it on remote sensing as well. So yeah, but for the Fourier transform is definitely useful. It depends on how much data you have, how computer intensive you want to make the process, and I mean things. That is very subjective thing. Depends on the application. Can we also log in, and is it free? Login means, I mean, you can log in to all these given websites which I discussed. Yes, they are all free, and you just need to register, and you can download data. Is there any must requirement for registering in USGS and other likewise data sources? No. There is now nothing like a must requirement. You just need to give some, you fill the form given, which is very simple, and it needs just your email, country and all. But what is going to be most important thing is your email. So very simple form, and you can download data, and it's definitely many data sets are free. Those which are not free, you will anyways have. Some are like you have to write a small project, you have to give description what are you going to use it for. So then they give it after some time, they send it to you. So it depends on what data you are looking for. But those data which we discussed, yes, they are free. CASE is generally specialized course. It will make you specialized, but you don't have to have a particular specialization to be a GIS specialist. So like you can be from any discipline, but you learn through it. I mean, so we teach like geospatial technology. We teach you, or anywhere you learn how to use spatial images and how to interpret them, how to explore the whatever parameter you are interested in and combine them and extract interesting information. These things you need to learn, and you're good to go. So you are specialized after you learn the tool, but you don't have to have some specialization before you start GIS. Okay, now the next question, which one open source software can be used in processing remote sensing data? So if you are good in computers, you can start with R, which is very user friendly and very popular in remote sensing or in GIS field. If not, then you can use also QGIS. QGIS is more like a GIS tool, not remote sensing. But like what I was trying to show you was remote sensing data. But I mean, to do GIS, you need remote sensing is just a data. What we are going to do with the remote sensing data set is GIS. So that's why you need to learn first of all how to get it and how to read it. Once you read it, it's in that software. Whatever you are going to do processing, this is the GIS. We are going to combine different layers. We are going to maybe manipulate the data, and that's that you can do in QGIS also, which is similar to GIS. Like you open it and it's similar to ArcGIS, but it's not meant for remote sensing application. It's GIS. Otherwise, R is very useful, especially layer stacking and ULC classification. Yeah, you can do these things in ArcGIS and I suppose in QGIS as well. But R is a better bet. It's something if you want to work on, it's definitely a better thing to do. What is the scope of GIS? Oh, there's a world. Like you can do so many different things from GIS. Should I start it? So this is interesting. We can say for different, like even for your when we talk about this industry application, insurance companies, they don't know what if there some hazard, if some calamity happened, they have to pay. Now the insurance company want to know how much premium or how much premium they have to set for this region because this region is prone to this part, or how much funds they have to allocate because this thing happened. Now before they start to fix the premium for this region, for any region, they use GIS, understand what should be, because see, I think this happens in India as well. At least in US, if I buy a car and I'm living in one place, just maybe 500 meters from other places, it falls in another block or in another county or any other distinct administrative boundary. Because this boundary was defined by some parameters using GIS, that this region people are more prone to accidents. So I will have to pay more premium than my 500-meter close neighbor, because he falls in different administrative boundary where the accident-prone category is relatively less. So insurance company define my premium using GIS, and it's just a small example. I mean, there's so many I can find like class of it. So now, which is the best job-oriented India research area in the field? In this field, you are talking about research job. So I think research job, I mean, you can work in academia, you can work in even in industry, like you work in GPS companies, like Trimble, all these kind of companies. I mean, with this opening of geospatial, relaxing of geospatial conditions in India, there are so many possibilities. Sorry? Okay. So, there are so many opportunities. I think navigation is a big potential. Also, now this automatic car, all these things are coming in. So this is image processing has a big potential. I mean, research is always evolving. So you can there's the geohazards and so many people are now interested in climate change, not because they are interested in knowing, but because it is affecting them. And that's why industries are now taking this. They are trying to know what is going to happen tomorrow. So they are interested in having candidates which can do these kind of research. So there are so many windows to go for. So can we also observe planets? Oh yeah. I mean, of course, there are many missions sent by NASA, and even we are trying. Like we went for Chandrayaan, we are trying for Mangalyaan, and NASA sent multiple missions to Mars, and there are multiple extraterrestrial missions sent by NASA. So, of course, there are things happening outside Earth as well. And this extraterrestrial science is also exploring big time. But we in Amrita, we are right now more focused on Earth and Earth exploration. So our team is expert in Earth sciences. Because of time, I don't know how many more questions we can take. And so what do you say?
So yeah, I think we've had a good amount of questions. Maybe one or two more questions. If you have any, please raise your hand. We can even give you the voice. We can enable your mic. But I suppose people have exhausted all their questions because we have quite a few. Anybody else has a question? So while we are waiting, I would also like to say that we have posted the feedback form in the chat window. Please fill up that feedback form, and based on that, we would email you your participation certificate in the webinar. So please don't forget to fill up the feedback form that we have posted in the chat window. I suppose there are no further questions.
Yeah.
So let us, thank all the participants. Is there a question?
There's one, sir. There's one. Yes. So, ma'am, could you please tell us about some must skill sets before a career in this field? As I said, it's not must, but having computer science, having a bit of mathematics is a plus. So, yeah, I would say must is your dedication, and you should be striving to learn, because you have to learn. Whichever discipline you are coming from, you will have to learn a lot, because it is a very, very multidisciplinary subject. Whichever discipline you are coming, you will have to learn other disciplines as well. So that's why more than expertise in any technology, you have to have a very hardworking temperament. You have to have you have a zeal to learn. That will make you expert in this, because you will have to learn not only computer science, mathematics. You'll have to learn earth sciences. If you're coming from technical background, you have to learn the science side of it. Then we have artificial intelligence, we have IoT, all these subjects including in it. So, yeah, there's nothing like must, but having computer science and mathematics helps.
Any other questions? So I guess we can wrap up.
Yes.
Thanks again, Alka. It was very informative webinar, as you could see from the response from the audience. And we would also like to thank all the audience for attending the webinar. And once again, do fill out the feedback form, and we would be emailing the participation certificates to you. So thanks one and all. Thanks for the organizers also, Sai and all the others. So with that, I guess we can conclude.
Yeah. Thank you, everyone, for joining us.
So Sai, we can close the session.
Yeah, sure.
Or maybe you want to keep it live for the feedback form for some time, or? Okay, I guess, Alka, we can leave. Maybe, the session can be on so that people can still go to the feedback form. And, even if there are questions, you can just post it and we can, answer it offline to you, no problem. So we'll leave it on for some time.
Yes.
And then Sai will decide when to close it. And so we can sign off. So
All right.
Thanks again.
Yeah.
Thank you.
Thank you, sir. Thank you.